Prior to beginning the activity, please be sure to review the faculty information and disclosure statements, as well as the learning objectives. After listening to the activity, complete the post-test by clicking the Earn Credit link in the episode description. Downloadable slides and resources are also available. The following presentation is copyrighted by Medscape. No use, broadcast, or recording of this presentation or any part thereof is permitted without the written authorization of Medscape.
The following presentation is part of a certified educational activity provided by Medscape Education and supported by an independent educational grant from Bayer.
Welcome to this Medscape program titled The Rise of the Machines, a quickfire exploration of artificial intelligence and big data in oncology. I am Marcela Prelai. I am a medical oncologist and head of the Artificial Intelligence Lab at Istituto Nazionale Tumori of Milan in Italy.
And I'm Ravi Parikh. I'm a medical oncologist and assistant professor of medicine and health policy and director of the Human Algorithm Collaboration Lab at the University of Pennsylvania in the US. So just to explain, this is a Medscape quickfire, which means we'll just have 30, 60, 90, sometimes 120 seconds to answer each other's questions. Are you ready? Great. Okay, so let's get started. Arcella, first for you, what is artificial intelligence? And you'll have 30 seconds to answer.
So, according to the Oxford English Dictionary definition, artificial intelligence is the capacity of computers or other machines to exhibit or simulate intelligent behavior. So, practically, this refers to technologies that can extract insights or patterns from large collection of data, producing outputs previously thought to require human intelligence. Machine learning and deep learning are the most important fields, but also recently generative AI, such as large language models.
Okay, you made it.
Let's move on to our first official topic, which is very interesting and is called image-based AI, starting with radiomics. So, Ravi, what are the uses of AI in radiomics? You have 60 seconds to answer to this question.
Great. Well, I think first it's helpful to just identify what is radiomics. And I think about it as the extraction of a large number of quantitative features from a patient's medical imaging, and then building predictive models around those extracted features. Sometimes there are hundreds or thousands of features that you can extract from regions of interest in a given scan. You can build predictive models to identify patterns and associations, oftentimes not discernible by a radiologist, but sometimes just approximating what a radiologist would call. And these are really intended to support patient-specific treatment planning, for example, radiation planning, or decision-making like what dose of systemic therapy to use. Now, if we think about some of the applications of radiomics, we can think about cancer screening, like detecting lung nodules from a screening CT, therapy response prediction, for example, predicting response to an immunotherapy in lung cancer, or automated detection of disease response for trials, like approximating RECIST criteria. And all of those are appropriate examples.
Thank you very much. So what is the common example of AI in radiomics? You have also 60 seconds for this answer.
Great. Well, I think I mentioned a few in the previous answer, but I wanted to delve down into one in particular. And this comes from a study that I was fortunate enough to participate in and presented this year at ASCO. And so we derived a deep learning biomarker from individuals' CT scans done at the time of initial staging for individuals with metastatic non-small cell lung cancer without actionable mutations. And so you can see that, that biomarker, you can identify individuals with a high likelihood of predicted response to immunotherapy indicated in the blue versus individuals with low likelihood indicated in red. What we actually found was that when we validated that algorithm in both real world and clinical trial data sets, we were able to identify subpopulations that actually had much greater likelihood of response to immunotherapy, potentially serving as an adjunct to our traditional biomarker-based risk stratification paradigms. So that's just one example. Okay, great. So let's move on to another hot area in artificial intelligence, which is pathology, another area of so-called computer vision. So Arcella, can you tell us what are some uses of digital pathology and AI in cancer diagnostics? And this time you'll have 90 seconds.
comparing to radiomics, digital pathology also used really deep learning methods to extract features and also to analyze the features. And so we can speak about simple tasks, for example, as pattern recognition in this case. So it's important to see how they identify patterns and features that indicate presence of cancer cells, for example, or classify different tumor types. But we have also difficult tasks, such as quantifying pathology-based biomarkers in tissue, such as TMA signature, for example, which the pathologist cannot see with the eye. And also identify the genetic markers is this new area, which is so-called pathogenomics. But let me give also some examples for example, PathAI, it's an example. Also, MSI Intuit, for example, it's an AI diagnostic that provides a pre-screen approach to detect MSI colorectal cancer tumors. So digital pathology can also be useful to drive treatment prediction, for example, immunotherapy non-small cell lung cancer, such as I3Lung. This is an international project that I am coordinating. But also another example is Artera. Artera helps to identify pathology-based biomarkers in prostate cancer to see if they respond to hormonal therapy. So finally, don't forget that also PathChat 2, for example, which is a visual language tools, are AI copilot tools, which can be really useful to summarize and create pathology reports from a microscope, slide viewer, or smartphone.
Great. There's obviously a ton of applications there. I'm wondering if specifically, we have a lot of biomarkers that we use from tissue-based or blood-based sources in clinical practice. How do you think about the uses of digital pathology compared with some of those traditional next-generation sequencing type assays? And can you give a specific example? And you have 60 seconds.
Oh, thank you. So this is a really hot topic, and we'll really, for different reasons, maybe change our practice and in our AI augmented development biomarkers. So, for example, I can give you an example on the identification of rare genetic alterations of BRAF and TRAC. For example, these authors, they used histochemistry stain thyroid tumors, and then to train, for example, deep learning models to detect BRAF mutations and NTRK fusions. They implemented an attention-based multiple instance learning classifier and assessed their their algorithms, and to generalize it in 3 independent cohorts. The model was able to detect both drivers and with this approach. And this is just one example. There are many of them that will come up in the next future. So, and now a more, let's say, general image-based AI question. Perhaps you can start, Ravi, and I will take over. So what are the advantages and limitations of imaging-based AI? So we have in total 120 seconds.
Great. Well, I think one of the key advantages is from the example that you just mentioned. I mean, think about how long in our practice it oftentimes takes to get a NGS report, to detect an NTRK or BRAF mutation. So if we're able to detect those instantaneously from pathology with a validated AI tool, that could result in faster treatment and better treatment for a lot of patients. So I think that's just one example of a big advantage. Another advantage for computer vision based radiomics, pathologyomics kind of assays is that the images can be shared quite widely, and there's a lot of them that can be shared by electronic medical records to train these. Obviously, they, as I mentioned, they have instantaneous viewing for clinical utility, and these are really efficient tools. They can view multiple images at once and give a holistic sense across the tumor rather than these pieces of tissue that we often get when we use our traditional biomarkers. And so there, I think there can be a lot of possibility. And cost, I mean, these things no doubt are costly, but they provide opportunities for better, potentially more cost-effective management if we're getting better diagnosis. So I had the easy part, talking a little bit about advantages. Marcela, you can talk a little bit about limitations.
Yeah, I mean, we know that across all these advantages, obviously there are limitations. For example, AI-based approaches obviously relay the quality and quantity of the data. We need data, we need volume, and volume is the main thing, and quality are 2 main things for big data. But also, for example, from deep neural network, these can be very difficult to extract and also to interpret. Also, there is a limited access to all these well-annotated data set, what we have done until now. So it's a very, let's say, limited to have and to digitalize and annotate these data. At the other hand, obviously these algorithms are time consuming, and we need to think about the cost because and they have a financial cost, for example, the equipment, the softwares, but also we need to think who is going to reimburse these costs. So these are the main ones.
That's a great point. Yeah. So let's move on to our next topic, which involves another hot topic, AI in drug discovery and development. So thinking about the questions, this is first for you, Arcella. How can you think about AI being used in the design and discovery of novel therapies? And you'll have 60 seconds here.
Also, this is a very great area, which I think it's an exciting area. So let me just summarize and 2, 3, 4 points that are very, very relevant in this field. So for example, optimize molecular properties for drug design by predicting how proteins fold and interact with potential drug molecules. This is an example. And AlphaFold 3 was recently published. It's a very interesting to explain it. Another example is AtomWise. You have heard about it, the virtual screening of large compounds libraries to predict which molecules will bind effectively to drug targets. And obviously, you reduce the time of the initial screening. Some papers said that from 18 months, you go to 6 months, for example. And also the de novo drug design. Now you generate these new virtual molecules instead of starting now from scratch in the real life. So in silico medicine, for example, is another example. However, also mining large databases from drug libraries and the real world data, for example, can help to identify also new market access opportunities for drug and potential repurposing. The every cure, for example, is one of them.
Great points.
Another interesting point here, Avi, is what and how AI enable clinical trial design. So you have 60 seconds for this answer.
Yeah, well, obviously, clinical trials underlie a lot of what we do in academic and community health centers. And, frankly, clinical trials are bringing drugs to market through clinical trials is a very inefficient process, oftentimes requiring 8 to 10 to 15 years when they could be much shorter. And so I think there's sort of 3 or 4 big areas where there's opportunities here. One is using real world data and digital twins in silico trials to actually assist in sample size determination and design of some of these trials. Which control group should we be comparing to? How should we be combining different drugs? Part of the issue there related to that is trying to identify optimal targeted dosing using precision medicine, artificial intelligence-based solutions, which is oftentimes a big limitation to traditional clinical trial design where we have a fixed dose. Another area, I have a hard time oftentimes identifying which patients are eligible for the right trial. And so using large language models to mine unstructured text and electronic health records to identify those patients at the point of care would be really helpful for me. And then the last thing, and I know I'm over time, I'm sorry, it's a hot area, is around using automated EHR feeds and natural language processing, oftentimes these EHR to EDC solutions, to help automate the extraction of information, because it oftentimes takes clinical research coordinators, hours, days to sort of extract information from clinical text regarding outcomes or adverse events that could be done in a much more efficient manner. So I owe you 15 seconds. Sorry about that, Ursula, but that's a little bit what I.
No, I know that you are over, but I will add something which is very interesting. So let me say that in the top that you said, 83% of the clinical trials do not go to a market access. So this is very important and a key topic.
Another important area there is even though more than half of patients with cancer want to participate in a clinical trial, only about 5% actually do. And that's a failure on our part for not identifying which patients ought to be enrolled in certain trials, whether they be diagnostic or therapeutic. So obviously a very important area. We're going to move on to our final topic, which is identifying the impact of AI on clinical practice, your day-to-day oncology care. So related to that, what do you think about how AI can improve clinical practice, Arcella? And you'll have 60 seconds.
So I utilize 1 hour, not 60 seconds, but
yeah.
joking, just to say that this is our main goal as medical oncologists also interested in AI. So, but just let me mention you some of these points. So, for example, it can be really to prioritize and give us a lot of efficiency. Imagine aggregating information to automate tasks. A key example, not here in EU, but in US, for example, the prior authorization letter in United States, it takes a lot of time. But also help in synthesizing, for example, peer review or literature, such as with using ChatGPT-4. We are doing it every day. But important things here, building clinical decision support and clinical decision-making systems. So, for example, for better diagnosis and better treatment selection, I'll take an example. Imagine, for example, when we don't have a primary site, and we can obviously detect it with the AI. But also, for example, the wearable device that use AI cognitive senses are very, very relevant to monitor the patients for their toxicity and their quality of life. So, and now I think this is the last question, but is one of the most interesting ones. So, what do you think, Ravi? It's going to be in the future the biggest issue in AI. So, you have 60 seconds.
Well, you hate to kind of be a Debbie Downer when there's all this potential, but I think there's sort of 5 areas that there ought to be some key advances in moving forward. So one is around the potential for AI to get it wrong, particularly in the area of large language models hallucinating about potential outputs. That could have big impacts if our patients or clinicians are using it for decision support. The other thing to realize is these tools oftentimes can drift in performance over time, especially as you get farther out from when they're trained, and they can be biased. So figuring out ways to proactively monitor and measure that is really important. Explainability is key. I'm unlikely to trust even a very accurate AI if I don't understand what's going on under the hood. And so we need to develop methods of explainable AI. That's a methodologic area. FDA regulation has to be responsible for all of these, and EMA regulation in Europe. And so we need to develop good regulatory paradigms, and the EU AI Act is one example of advances towards that. And then the last thing is just becoming aware, integrating AI into the overall education process, not having separate AI courses, but integrating artificial intelligence oftentimes into our traditional disease-based pathophysiology or our clinical courses, because we're all going to be using it in the future, and we shouldn't just be separating docs into those who use AI and those who don't.
Finally, maybe we can build our bubble towel at the
Yes.
end. Everyone speak the same language, so.
Absolutely. So we are officially out of time. This has been a great discussion, a ton of fun. I think we're happy to have another one because there's a ton of stuff to talk about with AI, and it'll all be different next year. But thanks for joining us today, and thank you for participating in this activity.